Okay, we're in 11.3 of Barnett, which is derivatives of products and quotients. And in fact, those are the two goals of this section. It's for us to be able to take the derivative of a product of two functions, as well as the derivative of a quotient of two functions. So why don't we take a look here at theorem 1, which is called the product rule. It deals with taking the derivative of a product of two functions. So if you have a function little f, which can be written as the product of two other functions, capital F and S, and if the derivatives of those other two functions, capital F prime and S prime, exist, then the derivative of our function, little f, is simply the first function f times the derivative of the second plus the second times the derivative of the first. That's why we label it f and s. This stands for first and second. In other words, the derivative of a product of two functions is the first times the derivative of the second plus the second times the derivative of the first. Once again in words, the derivative of the product of two functions is the first function times the derivative of the second function plus the second function times the derivative of the first function. As a quick example, what I like to do with these is right off the bat to try to figure out what my two functions are that multiplied together give me the product whose derivative I'm looking for. In this case, I'm looking for the derivative of y, and y is clearly a product of two functions. This is my f of x, and this is my s of x. What I like to do next is write those out on the side and take their derivatives. So the first function is f of x equals 5x squared. Its derivative is 10x. The second function is the polynomial x cubed plus 2. Its derivative is 3x squared. So now that I have those written out, all I have to do is plug them into the product rule. And according to the product rule, the derivative of this function is going to be the first function multiplied by the derivative of the second plus the second multiplied by the derivative of the first. Right? Notice the first times the derivative of the second plus the second times the derivative of the first. By the way, it doesn't matter if you switch the order in which you add those two. In other words, you could start with the second times the derivative of the first, and then to it add the first times the derivative of the second. It won't matter. Let's keep going here, and now all we have to do is plug in. F is 5x squared, s prime is 3x squared, s on the other hand is x cubed plus 2, and f prime is 10x. So I have plugged in, and I could simplify this a little, right? Y prime is going to be 15x to the fourth plus 10x to the fourth plus 20x. I distributed my 10x here. That's how I obtained those two. Notice I could combine the like values to get an answer of 25x to the fourth plus 20x. And that's how you use the product rule. Let's verify that we get the same answer here. And here it is typed out to make sure that you guys could see this well. So double check the work. And instead, let's jump to theorem 2, the quotient rule. The quotient rule deals with taking the limit, or taking the derivative is what I meant to say, of a quotient. So for example, if our function f could be written as some quotient n of x over d of x. In other words, f of x is made up of a numerator function n of x and a denominator function d of x. That's why they use n and d here. And if those two derivatives, n prime and d prime, exist, then the derivative of f is given by the formula here. D times n prime minus n times d prime all over d squared. In words, the derivative of the quotient of two functions is the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. That's a lot to say. In words, it's quite wordy. But the formula is very helpful, as we could see in the following example. Find the derivative of y equals 3x over 2x plus 5. Here it is written as a fraction, or as a quotient. So again, you could call these n and d if you'd like, but I prefer to call them t and b, because it stands for top and bottom. It really doesn't matter. You could stick to n and d if you prefer. You could use t and b. You could call them whatever you want. I'm going to do the same thing here that I did for the product rule. On the side, I'm going to write t of x and b of x and take their derivatives. So if t of x is 3x, the derivative of that is 3. If b of x is given by 2x plus 5, the derivative of that is 2. And that's all I need in order to use the quotient rule. According to the quotient rule, the derivative of my function is going to be the bottom multiplied by the derivative of the top minus the top multiplied by the derivative of the bottom all over the bottom squared, right? Again, I use t and b, they use n and d. It's really the same thing at the end of the day, right? You could think of this as n and d. It would look like that. So this now becomes a plug-in truck problem. All we have to do is just plug in the appropriate values. 2x plus 5 for b, the derivative is 3 of t, minus 3x, which is t, times the derivative of b, which happens to be 2, all over 2x plus 5 squared. These are always tricky to simplify. My suggestion is to keep the denominator as is, squared, and try to simplify the numerator as much as you can first. So when I distribute this 3 here, right, then I get 6x plus 15 minus 6x all over 2x plus 5, the quantity squared. Notice these will cancel out, leaving me with 15 over 2x plus 5, the quantity squared. And if we did everything correct, the answer should match up with the typed out solution here, and it does. So double check this with the n and d notation, and make sure that you understand every step. Okay, one last topic here in this section is an important one. It's one of the reasons, one of the biggest applications, I should say, of derivatives, and it's finding the equations of tangent lines. So for example, given some function like this one, it's a product of binomials, we want to find the equation of the line tangent to the graph of f of x at x equals to 3. So you have some curve, and at some point of tangency, you have a tangent line. You want to find the equation of this line. That's what it means to find the equation of the tangent line, right? And they gave you the x-coordinate for this point. In this case, it's 3, right? And they didn't give us the y-coordinate, but we could find it by just plugging in. So why don't we go ahead and take a look at how to do this? Well, you might remember that one of the applications of the derivative is that it's the slope of the tangent line. So first, we find the derivative of our function. And notice, this is a product. You could think of this as the first, and this is the second function. So we're really multiplying two functions of x in order to obtain little f. So we use the product rule to find our derivative here, and our derivative ends up being this. Why do we care about the derivative? Because f prime of x is the slope of the tangent line at x, right? That's one of the bigger applications of derivative, tangent line at x. Then we find f of 3 and f prime of 3. We want the equation of the tangent line when x is equal to 3. Thus, when we plug in 3 into the derivative, we get 12, and we know that our line looks something like this, y equals 12x plus b, right? Because any line could be written as y equals mx plus b, where m is the slope. So that's how we get that 12. But now how do we find this b? Well, we need a point on our line. And that's why we find f of 3 here, which is negative 45. Right? This tells us the point 3 comma negative 45 is on the graph. Why do we need this? Because we know how to find the equation of a line knowing its slope and a point on the line. We could use the point slope form, which is what they did here. You could also use actually a point slope form as well by just plugging in x and y, right, into the y-intercept is b here, right, into this form. But it really doesn't make a difference which form you use. So using y minus y1 equals m times x minus x1, knowing the slope is 12, and that the point 3 comma negative 45 is on the graph, we obtain the equation of this line, 12x minus 81. So in summary, we learn how to find the derivative of products and the derivative of quotients using the product and quotient rule, and we applied this to finding tangent lines in this section.